Exploring the depths, an introduction to sonar. Have you ever wondered how we explore the vast, dark depths of our oceans? How do we map the ocean floor, locate shipwrecks, or even find schools of fish? The answer lies in a fascinating technology called sonar. Sonar, short for sound navigation and ranging, is like a flashlight that uses sound instead of light to see underwater. Imagine yourself in a completely dark room. You can't see a thing, but you can still navigate by clapping your hands and listening for the echoes. That's essentially how sonar works. It emits sound waves that travel through water, and when these waves hit an object, they bounce back as echoes. By analyzing these echoes, sonar devices can determine the object's distance, size, and even shape. Sonar has revolutionized our understanding of the underwater world. It's an indispensable tool for oceanographers, marine biologists, geologists, and even treasure hunters. From mapping the ocean floor to tracking marine life, sonar plays a vital role in unraveling the mysteries of the deep. So, let's dive into the world of sonar and explore how this remarkable technology is shaping our understanding of the blue planet. Sound waves, the unsung heroes of sonar. At the heart of sonar lies the incredible power of sound waves. Sound waves are vibrations that travel through a medium, such as air or water. When you speak, strum a guitar, or even clap your hands, you're creating sound waves that propagate through the air and reach our ears. In sonar, these sound waves are generated by a device called a transducer. The transducer converts electrical energy into sound waves, sending them out into the water. These waves travel outward from the transducer, much like ripples spreading out from a stone thrown into a pond. When these sound waves encounter an object, they don't simply disappear. Instead, they bounce back, creating an echo. This echo carries valuable information about the object it encountered, such as its distance, size, and composition. By carefully listening to and analyzing these echoes, sonar devices can paint a detailed picture of the underwater world, even in complete darkness. It's like having an extra sense that allows us to see using sound. Sonar in action, from submarines to fish finders. Sonar's applications are as diverse as the ocean itself. Submarines, for instance, rely heavily on sonar for navigation and target detection. By emitting sound waves and analyzing the returning echoes, submarines can navigate through murky depths, avoid obstacles, and even locate other vessels. Fishermen also utilize sonar technology to locate schools of fish. Fish finders, as they're commonly known, emit sound waves that bounce off fish and other underwater objects. By analyzing the returning echoes, fishermen can determine the depth, size, and even species of fish in the area. But sonar's reach extends far beyond submarines and fishing boats. Marine biologists use sonar to study marine life, track whale migration patterns, and map coral reefs. Geologists employ sonar to map the ocean floor, locate underwater volcanoes, and study plate tectonics. Sonar is even used in archaeology to locate shipwrecks and uncover secrets of the past. From the depths of the ocean to the shallows of lakes and rivers, sonar is an invaluable tool for exploring and understanding our watery world. Frequency and echo unraveling, the secrets of sound. To fully grasp the intricacies of sonar, it's essential to understand the concepts of frequency and echo. Frequency refers to the number of sound waves that pass a given point in 1 second. It's measured in hertz, Hz. Higher frequency sound waves have shorter wavelengths and are used for detailed imaging, while lower frequency waves travel farther and are suitable for mapping large areas. Echo, on the other hand, is the reflection of a sound wave off a surface. When a sound wave encounters an object, some of its energy is reflected back towards the source. This reflected sound wave is what we perceive as an echo. The time it takes for the echo to return to the sonar device provides crucial information about the object's distance. By analyzing the frequency and timing of the echoes, sonar devices can determine an object's size, shape, and even composition. For instance, a hard, smooth object like a metal shipwreck will produce a different echo than a soft, irregular object like a school of fish. Understanding frequency and echo is key to unlocking the full potential of sonar technology. It allows us to interpret the language of sound and gain valuable insights into the underwater world. Gap 3S, Nature's Sonar Bats and Dolphins. Exploring the wonders of echolocation. While human-made sonar technology has revolutionized our understanding of the underwater world, nature has long since mastered the art of sound navigation. Two remarkable examples of natural sonar systems are found in bats and dolphins. These animals have sophisticated echolocation abilities that allow them to navigate, hunt, and communicate with astounding precision. Bats, often shrouded in mystery, emit high-frequency sound waves that bounce off objects in their environment. By interpreting the returning echoes, they can detect the size, shape, and distance of obstacles and prey, even in complete darkness. This biological sonar system is so refined that bats can differentiate between various textures and materials, enabling them to catch tiny insects mid-flight. Dolphins, on the other hand, use a series of clicks and whistles to explore their underwater surroundings. These sounds travel through the water and reflect back from objects, providing dolphins with a detailed acoustic map of their environment. Their echolocation abilities are so advanced that they can identify fish species and even detect objects buried beneath the seabed. The biological mechanisms behind these natural sonar systems are fascinating. In bats, specialized structures in their larynx produce ultrasonic sounds, while their highly sensitive ears detect the returning echoes. Dolphins, equipped with a complex nasal system, generate clicks that are focused into a beam by their melon, a fatty organ in their forehead. Their lower jaws receive the returning echoes, which are then transmitted to their inner ears and processed by their brains. Comparing these natural sonar systems to human-made sonar technology reveals both similarities and differences. Like bats and dolphins, our sonar devices emit sound waves and listen for echoes to create images of the environment. However, the precision and efficiency of natural sonar systems often surpass our technological capabilities. By studying these incredible animals, scientists and engineers continue to draw inspiration for developing more advanced and efficient sonar technology. Nature's sonar systems, perfected over millions of years of evolution, remind us of the intricate and awe-inspiring ways that life adapts to its surroundings. Bats and dolphins, with their extraordinary echolocation abilities, offer a glimpse into the wonders of the natural world and inspire us to push the boundaries of human innovation. Gap 3S. Section 5. Types of sonar, a glimpse into the world of sound navigation. Sonar technology encompasses a variety of systems, each tailored for specific applications. Two primary types of sonar are active sonar and passive sonar. Active sonar, as its name suggests, actively emits sound waves and listens for the returning echoes. This type of sonar is commonly used in navigation, fish finding, and underwater mapping. Passive sonar, on the other hand, doesn't emit its own sound waves. Instead, it listens for sounds generated by other objects, such as marine animals or submarines. By analyzing these sounds, passive sonar can detect the presence, location, and even type of objects in the water. Within active sonar, there are further classifications based on the frequency of sound waves used. High-frequency sonar provides detailed images but has a limited range, while low-frequency sonar can cover vast distances but offers lower resolution. The choice of sonar system depends on the specific application and the environment in which it's used. Whether it's active or passive, high-frequency or low-frequency, sonar technology provides a window into the underwater world, allowing us to explore, map, and understand this vast and mysterious realm. Section 6. Building your own sonar, a DIY adventure. Now that we've delved into the fascinating world of sonar, are you ready to experience the power of sound navigation firsthand? You don't need sophisticated equipment or a research vessel to experiment with sonar principles. With a few everyday items, you can create your own basic sonar device and explore the world around you using sound. This DIY sonar experiment is not only a fun and engaging activity, but also an excellent way to learn about sound waves, echoes, and the principles of sonar technology. It's a hands-on experience that brings the magic of science into your own home. Remember, safety is paramount in any experiment. Before you begin, make sure you have a clear workspace and adult supervision if needed. With a little creativity and curiosity, you're about to embark on an exciting journey into the world of sound exploration. Section 7. Gathering your sonar supplies. Everyday items for extraordinary discoveries. To embark on your DIY sonar adventure, you'll need a few simple items that you likely already have around the house. These everyday objects will be transformed into tools of scientific discovery, allowing you to explore the world of sound in a whole new way. Here's what you'll need: a large metal pot or bowl, which will serve as your transducer, emitting the sound waves for your sonar; a wooden spoon or metal ladle to be your sound generator, creating the initial sound pulse; a stopwatch or timer to measure the time it takes for the sound to travel and return as an echo; a measuring tape or ruler to determine the distance to the object you're detecting; and a notebook and pen to record your observations and calculations. With these simple items assembled, you're ready to step into the shoes of a sonar operator and explore the world using the power of sound. Gap 3S. Section 8. The science behind sonar performance. Discuss how water temperature, salt density, and other ocean properties affect sonar performance. Sonar, an acronym for sound navigation and ranging, relies on the transmission and reception of sound waves to detect objects underwater. However, the accuracy and efficiency of sonar can be significantly influenced by various ocean properties, such as water temperature, salinity, and pressure. First, let's talk about water temperature. Sound travels faster in warmer water compared to colder water. This is because the molecules in warmer water are more active and closer together, allowing sound waves to pass through more quickly. For example, if a submarine is operating in the warm waters of the equatorial Pacific, its sonar system will detect objects at a faster rate than in the colder waters of the Arctic. Next, consider salinity, which refers to the concentration of salt in the water. Higher salinity increases the density of seawater, which can also affect the speed of sound. In regions with high salinity, such as the Red Sea, sonar signals may travel faster than in areas with lower salinity, like the Baltic Sea. Pressure, which increases with depth, is another critical factor. As a vessel dives deeper, the pressure increases, compressing the water and allowing sound waves to travel faster. This means that sonar readings taken at greater depths will differ from those taken near the surface. These factors can create layers in the ocean known as thermoclines and haloclines, where abrupt changes in temperature and salinity occur. These layers can refract or bend sonar waves, leading to phenomena such as shadow zones where sonar signals are weak or lost. For instance, a submarine hiding beneath a thermocline may be undetectable by a surface ship's sonar. Understanding these ocean properties is crucial for naval operations, underwater exploration, and even for using fish finders in recreational fishing. By accounting for temperature, salinity, and pressure, operators can adjust their sonar systems to improve accuracy and reliability. In summary, water temperature, salinity, and pressure are key factors that influence the performance of sonar. Recognizing and adapting to these properties allows for more precise and effective use of sonar technology in various underwater applications. Section 8. Step-by-step sonar experiment, unleashing the power of sound at home. Now that you have your sonar supplies ready, let's dive into the step-by-step process of conducting your home sonar experiment. First, find a spacious area. Choose a large room or an open outdoor space where you can create echoes without obstruction. Next, set up your sonar station. Place your metal pot or bowl on a flat surface. This will be your sonar transducer. Then create your sound pulse. Stand a short distance away from the pot and strike it firmly with the wooden spoon or metal ladle. This will generate your sound pulse. Listen for the echo. Pay close attention and listen for the sound to bounce back to you as an echo. Measure the time. Using your stopwatch or timer, measure the time it takes for the sound to travel to a nearby wall or object and return as an echo. Calculate the distance, multiply the time you measured by the speed of sound, approximately 343 meters per second, and divide the result by 2. This will give you the approximate distance to the object. Experiment with different objects. Repeat the experiment with different objects placed at varying distances. Observe how the echo time and calculated distance change. Congratulations! You've just conducted your own sonar experiment using everyday materials. As we continue our exploration of sonar technology, let's delve into the range and accuracy of sonar systems. Sonar systems are capable of detecting objects at impressive distances, sometimes reaching up to 1,000 meters with an accuracy of +/1 meter. However, the effectiveness of sonar can be influenced by various environmental conditions. For instance, water temperature plays a significant role. In colder water, the range of sonar might decrease to around 800 meters. Conversely, in saltier water, the range could extend up to 1,200 meters. Depth is another critical factor. Deeper waters may cause variations in sonar performance. Understanding these variables is crucial for obtaining accurate sonar readings. By taking into account factors like temperature, salinity, and depth, we can better interpret the data collected by sonar systems and make more precise measurements. So, whether you're using sonar for marine exploration, fishing, or scientific research, remember that the environment around you can impact the results. With this knowledge, you can optimize your sonar usage and achieve more reliable outcomes. As we wrap up our journey into the world of sonar technology, let's explore an intriguing and highly strategic application: the Sound Surveillance System, or SOSUS. Developed during the Cold War, SOSUS was a top-secret underwater listening network designed by the United States to detect Soviet submarines. This vast array of hydrophones placed on the ocean floor could pick up the low-frequency sounds emitted by submarines, providing a critical edge in naval intelligence. But how does SOSUS work? Essentially, hydrophones capture underwater sounds, which are then transmitted to onshore processing stations. Here, sophisticated algorithms analyze the audio data to identify and track submarine movements. This system relies heavily on the principles of sonar technology, leveraging the propagation of sound through water to monitor vast oceanic expanses. Today, SOSUS has evolved and expanded its applications beyond military surveillance. Modern naval operations use this technology for various purposes, including maritime security, environmental monitoring, and even scientific research. For instance, SOSUS arrays have been repurposed to study marine life and detect underwater volcanic activity. The legacy of SOSUS highlights the immense potential of sonar systems in both defense and civilian contexts. By harnessing the power of sound, we have not only enhanced our security but also gained a deeper understanding of the ocean's mysteries. So, the next time you think about sonar, remember that its applications extend far beyond fish finders and submarines. From safeguarding our waters to uncovering the secrets of the deep, sonar technology continues to play a pivotal role in our exploration and protection of the world's oceans. As we conclude our deep dive into the fascinating world of sonar, it's crucial to address the ecological impact of this technology on marine life. While sonar has proven invaluable for navigation, defense, and research, it also poses significant challenges to various oceanic species and ecosystems. Sonar operates by emitting sound waves that travel through water, bouncing off objects and returning to the source. These sound waves can be incredibly loud, sometimes reaching levels over 200 decibels, much higher than the noise produced by a jet engine. Such intense sound levels can have detrimental effects on marine animals, particularly those that rely on echolocation, such as whales and dolphins. One of the most concerning impacts is on cetaceans. Studies have shown that sonar can cause disorientation, hearing loss, and even physical trauma in these animals. For instance, during naval exercises that use mid-frequency active sonar, there have been instances of mass strandings of beaked whales. Researchers believe that the loud sonar pulses disrupt the whale's ability to navigate and communicate, leading them to beach themselves in confusion and distress. Additionally, sonar can alter the behavior of marine species. Fish, for example, may abandon their habitats due to the noise pollution, affecting local ecosystems and fisheries. A study conducted by the University of Maryland found that fish exposed to sonar-like sounds exhibited increased stress levels and reduced reproductive success. This disruption can ripple through the food chain, impacting not just the fish but also the predators that rely on them for sustenance. Even invertebrates are not immune to the effects of sonar. Research has indicated that loud underwater noises can harm squid and octopuses, causing physical damage to their tissues and impairing their ability to hunt and evade predators. The scientific community is actively investigating ways to mitigate these impacts. One approach is to develop quieter sonar technologies that minimize noise pollution. Another strategy involves creating marine protected areas where sonar use is restricted, allowing sensitive species to thrive without the threat of disruptive noise. In conclusion, while sonar technology offers immense benefits, it is essential to balance these advantages with the need to protect marine life. By understanding and mitigating the ecological impacts of sonar, we can ensure that this powerful tool continues to serve humanity without compromising the health of our oceans and the diverse species that inhabit them. Thank you for joining us on this journey through the world of sonar. Remember, our exploration of sound doesn't end here. Stay curious, stay informed, and continue to discover the wonders of the deep blue sea. As we delve deeper into the world of sonar, it's natural to wonder why this technology is used underwater, while radar dominates the skies. The answer lies in the fundamental differences between sound and electromagnetic waves. Radar, which stands for radio detection and ranging, operates by emitting radio waves. These electromagnetic waves travel through the air and bounce off objects, allowing us to detect and locate them. However, radar waves are absorbed by water, making them ineffective for underwater detection. This is why radar is not used in water. On the other hand, sonar, or sound navigation and ranging, uses sound waves. Sound waves travel exceptionally well in water due to the medium's density, allowing sonar to effectively detect objects and navigate underwater environments. This makes sonar the preferred choice for submarine navigation, underwater mapping and marine research. But why isn't sonar used in the air? The answer is simple. Sound waves dissipate quickly in the air and are less effective over long distances compared to radar waves. In the air, radar waves can travel vast distances with minimal loss of energy, making them ideal for applications like weather monitoring, air traffic control, and military surveillance. In essence, the choice between sonar and radar comes down to the medium in which they operate. Water's ability to transmit sound waves efficiently makes sonar the superior option for underwater detection, while the air's suitability for electromagnetic waves makes radar the go-to technology for aerial and terrestrial applications. Understanding these differences helps us appreciate the specialized tools we use to explore and navigate our world, whether beneath the waves or high above the ground.